Okay, welcome everybody. We have today's session with two talks. First talk is on site, Thierry Giamarchi. Welcome.
Okay, so let me click on this to say that I agree that the meeting is being recorded. Okay, so before I start, I wanted to thank the organizers of this program, and of course, in particular, Misha, for the invitation. It's really a pleasure to be here physically in my former alma mater, less than whatever, 200 meters from my previous lab. Now, it's really a pleasure to be at this workshop, and I hope that you can hear me reasonably well through all the technology equipment that we have. The other thing we should see is working is the pointer, so I hope you can see the yellow pointer on the screen. And I'm going to give you a little bit semi-historical, but of course with new research results, overview on what I would call out of equilibrium impurities in 1D systems. There were already several talks dealing with polarons, dealing with the interaction of impurities, mostly in equilibrium. And I will try to sort of take you from there and go to the out of equilibrium part. So in principle, if this is working, no, doesn't seem strange, because the pointer is working, but for some reason I cannot pass the slides, maybe because I don't have the focus on the right window. So I should point out the people who actually, with whom I had the great fortune to collaborate on this problem. And of course, the two first heroes here are Misha and Vadim Sheyanov, because we started to interact. Actually, they dragged me into this field 13 years ago now, and I'm extremely happy that we had this fantastic collaboration on the impurity. I'll recall, of course, some of these works, and then I will also move to more recent works that we did with Adrien Cantian, Uli Scholvök, and Nosat Kama, who was a PhD student in my group. And I don't think the time will allow me to go very deep in another series of work, which we did both in collaboration with a group of Päivi Torma, in particular with Anne-Maria Visuri, who was at the time a PhD student of Päivi, then joined my group and is now in Bonn with Corinna. Francesco, oops, I forgot his first name, Marcel, Andrew Daly also. And then another series of work, which is a little bit marginal from the main focus of the talk, but that I want to mention with Baro Horowitz and Pierre Ledoussal. And last but not least, we had the pleasure to have fantastic collaborations with experimental groups, with a group of Francesco Minardi in Florence, and the group of Stefan Kur and Emmanuel Bloch in Munich. And I'll try to discuss also these collaborations. Okay, so what is this about? What is the problem? Well, the problem, you know, it's essentially the whole problem of the workshop. It's a single impurity, which I will denote by p square over 2m. It's a single object with mass m, which is coupled to a quantum bath. And I will totally specialize in this talk 1D quantum bath. And this is described by a 1D Hamiltonian. You take your favorite up. Okay, so is it better? Well, okay, let's try. Yeah, I'll switch it up like this. Okay, I feel like a cosmonaut. So you take whatever you like, 1D bosons, 1D fermion, Lieb-Lininger, Bose-Hubbard, Fermi-Hubbard. At that stage, I don't care. And the important point is that there is a coupling between the impurity and the bath, which is proportional to some local interaction strength V. And essentially, if X is the position of the impurity, of course, it's an operator which does not commute with P, with the momentum. This is simply measuring the density of particles of the bath at the position X of the impurity. So this is the problem we are trying to solve or measure. And of course, in equilibrium, this is what leads to the famous or infamous polaron in high dimension. And usually you try to compute renormalization of the mass and so on and so forth. Now, not to say that the question of the polaron is simple, but this is still equilibrium quantity. The impurity is well in equilibrium with the bath, but things become even worse when your impurity is not in equilibrium with your bath. And then we know that there are phenomena that occur, which goes by the name of Anderson orthogonality catastrophe. And these phenomena are especially important in 1D, and I will try to elaborate a little bit on this. So the kind of thing that we would like to discuss here is essentially the following problem. You have your bath of blue particles, which are doing whatever they want. And then at some point, you either convert the blue particle to a red particle, or you create a red particle, or you release a red particle at time 0, which you held fixed initially. You release it in the sea of the blue particle. All these things are out of equilibrium physics. You switch something at time t equals 0. Oops, that's very, very shaky. You switch something at time t equals 0, and essentially that sets a reference starting time for the problem. And then because you have only one red particle, you usually try to find where it is at time t. And this is, if you want, a local quench instead of being a global quench where you remove the whole lattice or you go from Mott insulator to superfluid and so on and so forth. If you are at with an impurity of infinite mass, you could imagine that nothing happens. You have your impurity, you create it, it doesn't move, you remove it. Well, that's it, nothing has. But we know it's not true, and this problem is very well known in condensed matter. It's called the X-ray edge problem, and this was pioneered by Mahan and solved essentially by Nozière and de Dominicis. And we know that what happens is actually that even if you create an impurity at time 0 and point 0 on the ground state of your blue bath, doesn't matter at that stage if it's 1D, 2D, 3D, and then you destroy it still at point 0 because it has infinite mass, it cannot move at time t. When you insert the operator which describes the time evolution, you see that you have to compute the average here of the product of the ground state by the exponential of two different Hamiltonian. This Hamiltonian is the Hamiltonian without an impurity. This Hamiltonian is the Hamiltonian with one impurity. And these two wave functions evolve very differently. And as shown by Anderson, they are actually orthogonal to each other. And therefore, this impurity, which does nothing except being switched on and off, is actually leading to a correlation function here, which decreases as a power law with an exponent which depends on many parameters of the system. So this is something which is quite remarkable. And normally, we don't care too much about this as soon as the impurity can move, because all these effects are supposedly destroyed by the recoil of the impurity. When the impurity moves, this is supposed to, let's say, diminish strongly this Anderson orthogonality catastrophe. But we know also that in 1D, this is not the case. So we really have to worry about such effects in 1D. And that's what makes, I think, these impurity problems especially interesting in 1D. By the way, I know it's not super convenient remotely and whatever, but if you have a question, so I'm not monitoring the chat. I don't know if Misha is doing it. Yes, so he says he's doing it. But don't hesitate if you have any question to ask it immediately rather than wait till the end of the seminar. Okay. Yes, sure. And if you're local, you will be thrown the cube.
How, like, is it important conceptually that you remove the impurity?
No.
Okay.
You could flip, for example, the color of one particle and then unflip it. You need to be able to go back to your initial ground state. So either you create the impurity and then you remove it and you go back to the ground state, or you change the color of one particle and then you change it back to a blue particle and you go back to a function where there is only the bath. Now, there are other correlation functions on which I will come later, where you don't remove the impurity, you create the impurity and then let it move, and you measure where the impurity is without removing it. These are actually more complicated to compute. So no, it's not necessarily. No other question at that stage? Okay, so let's continue. So how to treat? There are, of course, many methods that we will discuss as we move on. But I just want to point out what happens if you use one method, which of course I love, which is the bosonization technique. And I won't do anything to remind you what bosonization is. It's a reparametrization of 1D Hamiltonian in terms of collective variables. If you want, I can recommend you a very good book on the subject, but I won't do it here. And just to keep a long story short, any 1D Hamiltonian practically can be rewritten in terms of an harmonic oscillator type Hamiltonian here, which depends on two parameters. One is the velocity of sound excitation in the system. The other is a dimensionless parameter K, which contains the information on the interactions and so on and so forth. And this variable phi that is here intervening in the Hamiltonian is actually related to the density by a formula of this type. So you can say that the density at point X is the average density. Then take the p equals 0, p is an integer here, take the p equals 0 part here, you get just a gradient of phi. This is kind of the hydrodynamic description of the density. If you have particles, you can bring them at one point or remove them from the point, and you increase or lower the density. And then you have higher harmonics. If you take p equal 1, p equal 2, p equal 3, which oscillate at with a wave vector which is 2 pi rho 0, which is exactly the periodicity between the particles if they were crystallizing. And that tells you that in 1D, you can view anything a little bit as a charge density wave, as a crystal of particles. And the density will have trace of the fact that it might want, imagine a repulsion between the particle, it might want to form a nice crystal, a nice charge density wave. Of course, the crystal is not ordered because there is this field phi which is fluctuating like crazy and which destroys this perfect order. But nevertheless, you have these two components in the density. And now if you look at the dimensions of these operators, you see that there are two important things that appear. The Q equals 0, the grad phi is decreasing as 1 over x squared, and that's it. And the other parts, the higher harmonics, so the charge density wave harmonics, are decreasing with an exponent which depends actually on this Schlödinger parameter K. So you will have two different classes of systems depending on which one of these terms dominates. If K is larger than 1, then this term dominates. And you can forget about this kind of charge density wave aspect of the physics. You just have to worry about the long wavelength fluctuations of the density. And as we will discuss later, this is the case of bosons. For example, if your bath is made of bosons, then the Schlödinger parameter K is between plus infinity and 1. And therefore, you're totally in this class. On the other end, if your bath was made of spinless fermions or fermions with spins or whatever, then usually with repulsion, K is smaller than 1. If you have attraction, it's very much like bosons. But if you have repulsion, then K is smaller than 1. And then you see that you have a completely different problem where you can now neglect this grad phi, but then you have to worry very, very seriously about these higher harmonics, and they will sort of mentally represent a periodic modulation of the density on which the impurity will try to go through. And this has very, very different consequences. So I will discuss mostly the first case, but I will try to say a little bit something of the second case. So I will refer to these two cases as the boson-like and the fermion-like, but okay, that's just a terminology. So let's do first the bosonic type behavior. And this is the case we looked at with Misha and Vadim, I would say now a long time ago, but still within this century, so it's not too bad. And the idea was to try to understand what would happen if you had a two-component Bose gas with a spin 1/2 in a way. So, but fully polarized, because the Bose gas would have ferromagnetic exchange. So naturally, you get only spin up, which exists. And so this is the standard model where you get particle with a mass with an interaction between the particles. You can put longer range interaction if you want. It doesn't matter at that stage. Let me forget. And we know that there is a dimensionless parameter which describes the strength of the interaction. So think of gamma as the strength of the interaction. And of course, what was computed, this is in connection with the talk of Gregory yesterday, people computed the effective mass of one single impurity of spin down in a sea of spin up. And indeed, you find that this effective mass would grow as gamma, like what you would expect in a polaron-like system. So if you have something like this, the naive expectation is to say, I have a free spin down particle, which is surrounded by a cloud of spin up, and then it has this effective mass, and then it does what the particle with effective mass gamma is supposed to do. And then actually, this is not as simple as that. And one way to view it is to measure this correlation function, which is, it's not the creation of an impurity, but it's a slightly different correlation where you flip down one spin. So you destroy a blue particle, you create a red, and then you unflip the spin at another point at another time. So you destroy the red particle and make it a blue particle again. And if you use this bosonization technique that I was mentioning, actually the grad term that I was showing is really something which is linear in boson operators, which are the sound waves of the Wendy system. So this is very reminiscent of the original polaron problem, where you would get a particle which is coupled to phonons, a la Feynman, if I would say. Okay, so let's first discuss what would happen if the repulsion between the blue and the red particle are so large that the red particle can never cross a blue particle. So U is very large in the system, and I'm in what we called at the time the trap regime. Then you essentially have to compute. You can do a field theory analysis of this problem, and you can sort of compute the properties by saying, that you have essentially the trajectories of the bath, which are all allowed, and the trajectory of the red particle in space-time should be such that it cannot cross any of the trajectory of the blue particle. So you have to put an additional constraint to what otherwise would be a simple Luttinger liquid. And when you put this constraint, you can express it relatively simply. And what you find is the following result, which is that this Green's function that I showed, which is again, essentially creating the impurity at 0, 0, and destroying it at xt. Again, it's not exactly that, but it's not very far from that. Instead of being the one of a ballistic particle, which would arrive there with an effective velocity, or even a diffusive particle, is something that decreases like exponential of minus x squared divided by log of t, which means that when x squared becomes much larger than log t, this Green's function is 0. So this is a sub-diffusive particle. If you want, it's like if the particle was bumping forever between the two first blue neighbors and was never able to go much further. Of course, it's not true because the blue gas can drift on the right, can drift on the left. So it can move a little bit more, but extremely, extremely slowly. And this tells you that first, this has nothing to do with the Luttinger liquid anymore. It has nothing to do with a ballistic particle of effective mass m, and you should analyze the property of this system in its own right. So you have subdiffusive behavior, no Lorentz invariance, no power law, and of course, no light cone singularity, and so on and so forth. So this is a new regime. To go to the full solution was a little bit more complicated. There is no easy field theory or exact solution available. So actually what we did in the first paper was to do an ansatz for what would be the spectral function, the Fourier transform of this Green function, which was to say that at the end of the day, the whole spectral function looked like this, where you get a matrix element and then a delta function of the excitations. And here what you want is to say there is an edge in the spectrum. There is a minimum set of energy below which you cannot create excitations. And what we want is something which has a power law behavior close to the threshold, a little bit like in a Luttinger liquid, you would have something like this. So you want a spectral function which is only existing non-zero when the frequency is larger than the energy as a function of k, to some power, which is also potentially a function of k. The energy, because the particle is alone, has to be k squared over 2m star. And the exponent normally in a Luttinger liquid would have been a constant. But here, because of the k square, this exponent should include also the correction of other k square. And so we had finally very few parameters that were describing this effective spectral function. At the end, we had two parameters, alpha and beta, and amplitude, which I won't worry too much here. And the effective mass was the one which was already determined before. And now the idea was to match the alpha and beta from the solution in the trapped regime, which we had from the field theory. And when you did that, you had the general result, which was the one that I show here, which is interpolating between the subdiffusive behavior x squared is of the order of log t, and something which looks much more like a normal diffusive behavior, where x squared would be sort of in phase with t, but with slight additional complications that I don't want to discuss. So you see that here the right solution is alpha equals 0, and beta is actually a universal number which depends on the Luttinger liquid properties of the bath. Keep this in mind. The exponent here of the spectral function is going to -1, and then with a k square correction, because we will come back to that a little bit later. Here is a plot of this correlation function. I don't want to go too much in the detail here, but this is something which essentially show you that the poor impurity is very much localized by the effect and the interaction with the bath, and much, much more than if it had been a ballistic particle. And so this is an exciting new effect that is way beyond the polaronic physics that you would expect with the effectiveness. Okay. This was literally, you could say that Misha was the face that launched 1,000 ships, just like Hélène of Troy, because really, literally after this initial paper, there were many, many studies. I've listed some of them, both on the theory and of course on experiments. There were many experiments who started to deal with impurities, actually experiments that of course already played a little bit even before with impurities, but this was an exciting new direction to look at. This ansatz was validated and then extended in two other papers that I don't want maybe to go too much in details here, but to go to the Bose-Hubbard model, to do it on the lattice and try to find a more exact solution by mapping the Bose-Hubbard model to some form of the so-called TJ model, where you have a magnetic exchange, which is ferromagnetic between the particle of the blue bath, and then some kinetic energy term, which is describing the fact that you don't have one particle per site. So this particle can hop in the places where there is nobody. And I will cut a long story short, but when you compute with this technology, which this time is not an ansatz, but which is sort of a systematic derivation from the Bose-Hubbard model, you do find spectral functions which have exactly the behavior, the singularity threshold that was the one that I showed you before. So validating this ansatz that alpha equals 0, so the exponent is -1 plus a correction which is proportional to k square with a term which is dependent on the Luttinger liquid of the bath. There was a second and relatively complete solution that was obtained out of the Godin-Young model by using sort of the matching between Bethe-Ansatz and effective field theory. So the idea is that you have the Bethe-Ansatz solution of the problem, and then you say, what should be the effective field theory that I should build for my impurity? And you have to take the Luttinger liquid for the bath, but then you have to add these operators which describe the interaction of the impurity with the grad phi of the bath. And this depends on set of two parameters, two coupling constants, one for right movers, one for left movers, that you can actually extract from the Bethe-Ansatz. And then you have the formula which gives you the exponent, this delta of k that I showed before, -1 plus the correction. And actually, if you work out from the exact solution, the correction, you find this k-square behavior that was already mentioned. And you can even compute the correction to this behavior and obtain for this model the exact exponent, which I plot here. You see that when k goes to 0, the correction term, the alpha k, which is here, is really negligible compared to k-square. So you recover what the field theory approach was giving. Okay. Now, how this can or cannot be tested in experiments. So I'll tell immediately that this, to the best of my knowledge, and Misha, you can correct me if you know otherwise, has not been tested in experiments. I don't know any experiment which has tested that. But if you know, ask him. I ask you. No, maybe you want to say something after. But okay, if it has not been, it should be. So this is, of course, something which is quite remarkable and what we need to test. So let me show you two experiments which I know quite well because we were involved on the theoretical aspect of these experiments, which tested some aspects of what I am going to tell you, but not this, of course, Green's function and this exponent. And I'll try to explain maybe why a little bit later. So the first experiment was, as I said, in the group of Francesco Minardi in Florence. And this is a very nice experiment where they realized 1D tubes and they had potassium impurities, which were trapped in a light blade and then released by removing the green light here. They were released in a chain made of rubidium atoms. And they had a Feshbach resonance and they could control the potassium rubidium interaction from 0 to infinity, essentially. Now, everything was in a trap. You know that I hate the trap. I cannot say enough how much I hate the trap. But here, the trap had an interesting effect is that everything was thus an harmonic oscillator. And because the potassium atom was super confined at the origin, what happened when it was released is that the wave function expanded, then contracted, then expanded, then contracted. And so you could measure here the oscillations of the size of the cloud of potassium atoms. And if the coupling constant is 0 with the bath, here is the size of the bath. So you see that the size of the potassium atom can even go larger than the size of the rubidium. So this is little complication compared to an idealized situations where there would be potassium, rubidium everywhere. But these oscillations here were very well fitting what you knew from the initial size of the wave function and the frequencies of the trap and whatever. And then when you start putting coupling between the potassium and the rubidium, you see very clearly that, of course, these oscillations get lowered and get damped as the time goes. So this is clearly the effect of the interaction with the bath. So not only do you renormalize physical parameters of the system, but you give also a kind of lifetime to the oscillations that you would have in this system. Now, this is not the type of correlations that I discussed before. And so to try to analyze a little bit this, we went back to trying to compute the physical parameters of the system by saying that we will trace over the bath, which again is made of sound wave, sound excitations. And then you can use a variational approach a la Feynman to try to find a quadratic approximation for this horrible integrated action for the impurity. And this allows you to obtain, as a function of the parameter eta, the renormalization of the mass that you would expect for this. At the time when there was the experiment, the agreement was not super fantastic between these calculations and the observation of the effective mass. We took a simplistic model where you cut the modes for the bath at a fixed K. And as you heard yesterday in the talk of Grigory, in a study which came, I think, about 5 years later by Eugene and collaborators, actually taking just the K-square dispersion instead of cutting the modes give an excellent agreement for not too strong interactions between the bath, between the theory and the experiment. So this variational approach is actually a very good description of what is taking place in the system. There were additional analyses that were done, in particular by Laetitia Couliandolo and her PhD student, trying to take into account explicitly the parabolic trap. This is quite complicated studies, so I refer you to the literature if you want to know. But this is one of the earliest experiments who show this effect of damping in the oscillations between these two species. A variant on this experiment was done in the group of Stefan Kur and Emmanuel Bloch. So you have a 1D chain of, let's say, yellow atoms. Then you change at one point one yellow atom into a green atom, but the barriers are very high, so nothing moves. And then at time 0, you lower the barrier, and then everybody starts to move. Now, this is the quantum horse race, if you want. Of course, this experiment is essentially done easily if you have a Mott insulator of bosons. So you have one particle every side, in which case this is a simple problem because your particles are not really mobile. The yellow particles are not really mobile. So what you get is the propagation of a single ferromagnetic excitation. But this is something one can study, and this is something we did in collaboration, as I said, with them. And Adrien Cantillon was the driving force in the collaboration. And when we study this propagation, you see here some images of the experiment. The only thing which is seen is the position of the residual impurity. And of course, you have many systems in which you have defects that have to be eliminated, but you observe the propagation of the impurity at different times. And this is, of course, in very good agreement with numerical calculation. This is, as I said, a simple ferromagnetic Heisenberg model, but where it becomes interesting, so you expect the velocity of propagation is linked to the ferromagnetic exchange. And lo and behold, if you measure, you find that the velocity is indeed proportional to this ferromagnetic exchange, up to a point where the kinetic energy is large enough so that the bath is not in the Mott insulator regime anymore. And that would be the interesting regime to explore, but the systems were very short, 10 sites, about 10 sites. So this was, of course, difficult to test for more detailed things. So this is clearly an experiment that had all the ingredients to really test the more detailed predictions, but which would need a little bit more juice in size to be able to do this. What you see here is a very clear change of regime when you leave the Mott insulator. You see polaronic effects. This is something I don't want to discuss too much at that stage. I just want to pause here to make a sort of note which says that life is hard, because for theorists, we like to compute two-body correlations, like the one I mentioned. You destroy the impurity, you create the impurity at 0.0 times 0, then you let evolve, and then you destroy it at point x and time t, or you flip a spin and you unflip a spin. Actually, what is, quote, easy or more easy to measure in experiment are typical correlation like this. You start from the ground state, you create the impurity at point x equals 0, you let evolve, and then this is your wave function at time t, and then you measure the average of the number of the population of impurity at point X, sandwiched into this wave function. So this is a much more complicated correlation function to compute. I don't really know how to compute this one, except numerically, of course. As Anderson was saying, to resort to the indignity of numerical calculation. This is what he mentioned for Anderson localization. But I think this would be very nice, and workshops for like this one are good for that, to discuss, to see where we can touch ground between actually what we can compute and what can be measured. Because otherwise we'll never meet, or it will always be very difficult to meet. So I just wanted to make this note because I think it's an interesting okay, of course, there are many remaining problems and questions, and I will certainly not touch all of them. There are, of course, many other directions that I will not mention, like the driven impurities and things like this, on which I know practically nothing, but of course, you will have other talks during this workshop. I just want to mention that we briefly touched the kicked impurity in this collaboration with a group of PIV, essentially by studying one impurity numerically. This was purely numerical, studying one impurity in a bath of either fermions or bosons, giving a kick to the initial, to the impurity, and then measuring the center of mass of doublons, sites which were doubly occupied as a function of time. So I'll just flash one curve, and I'll be happy to discuss more if you want, but I won't say much more on this topic. What I would like to comment a little bit more on is a further study that we did, mostly numerical, but also some analytical component, to try to understand a little bit more this Green's function and what control this Green function. And this was done together with Adrien Cantillon and Uli Scholvach. And the idea was, again, that we have this spectral function, which is a power law of the difference between the frequency and the energy, p square over 2m, with this exponent, which is -1 plus a correction, which is going as p square. And actually, the question is, can we compute this relatively simply? And actually, what we found is that one method which works very well, the same way that it worked very well for the X-ray edge problem, is the so-called link cluster approximation, or expansion, if you want, which is a different way to resum the perturbation series. So essentially, you re-exponentiate the perturbation series, and you can show that the Green's function is written as this form here, where f is a resummed part of the perturbation series in the interaction between the impurity and the bath. And here it's what you get for this form f2, where essentially this function here is taking into account the excitations you can create. So if you want to make the impurity go from momentum P to momentum P plus Q, and then you have to excite a phonon in the bath to do this. So this is a very simple approximation. It's, of course, it has no reason to be valid regardless of the strength of the interaction. But for small interaction, one can wonder whether this approximation works well. And then we did a comparison with the DMRG. So here is a DMRG calculation of the Green's function at p equals 0. This is not x, this is p. As a function of time, you see it decreases as a power law, as it should. And then you can extract here the exponent out of the DMRG. And you can try to compare this with the predictions of the link cluster expansion. And as long as your coupling constant is in the interaction here is not too strong, you see that there is good agreement between the solid line, which is the link cluster expansion, and the predictions that the DMRG, which is exact essentially, is giving. So it means we can perhaps understand a certain number of things by looking at this link cluster expansion. And there, one interesting consequence that the link cluster expansion is giving us is that there are actually two regimes. We have this regime, which is this power law dominated regime, which I would call the infrared dominated regime. This is the regime where the particle is not able to excite real phonons in the system, just virtual phonons, and reabsorb them. And this gives this Anderson orthogonality. This gives the Green's function here, which is actually a power law. This is a double logarithmic plot. So you see here the power law type behavior. And this, of course, at p equals 0 is always a power law. There is no problem. But if you change the momentum, there will be solution where you can excite real phonons in the bath. And then this Green's function changes drastically and starts to decrease exponentially. And this is what you see here on the right. You see that for the green and the red curve, this is now a single logarithmic but linear here plot. You see that this is describing exponential decay, which is more corresponding to what you would expect for the polaron moving like a blob with a finite lifetime. And that you see that you have these two regimes that exist, and this is what the link cluster expansion gives. As a byproduct, we also sort of got a kind of interpolating formula. F is for fudging here because, okay, this is sort of made a little bit by hand. So this is a formula that is giving us the exponent, but not only at weak interaction. At weak interaction, U is very small, so arctangent is nearly pi over 2. You can expand, and you see that F disappears in this expression, but which is also giving us the exponent at very large interaction, where, of course, the link cluster expansion has no reason to work. And this surprisingly simple formula seems to work pretty well. Here you have the dots, the Giamarchi results, and the solid line is this interpolating formula. And I would say, at least at the level of the accuracy we're able to do the calculation, this seems to work pretty well. What is nice is that this factor F can be directly related to the size of the hole that the impurity has created around it. So this is an interesting effect. I'm not sure we understand it completely, but this is something that I wanted to show. And we tested for various parameters, various kinetic energy of the spin up and the spin down, and this formula works reasonably. Again, more questions than answers. One last thing that I would like to mention is the fact that we started to extend this type of physics and try to understand what happens when we are not in 1D strictly anymore, but when either the bath or the impurity becomes more 2D. And this was done with Noshat Kamar. Actually, it was his PhD thesis and in collaboration with Adrien. And the idea was to look at ladders, which is sort of the first step to 2D. And we started by a very simple calculation, or very simple system, I should say. Calculations were not simple, which is to have a ladder for the bath. So you have two bosonic chains. You have possibility of tunneling between the chains for the particles of the bath. But for the moment, the impurity is constrained to move only on one single chain. So the impurity cannot jump from one chain to the next, but has to stay on the bath. So now, why is it interesting? Well, it's interesting because contrarily to a single chain, where the bath is made of these massless modes, now, if you have two chains, you have this more complicated Hamiltonian, and then you see that the transverse degree of freedom, the phase between the two chains here get locked by this term, by this cosine, which is like usually in bosons, you would like to have the same phase on both chains. And therefore, this is enough to open a gap in the spectrum, but only for half of the degrees of freedom. So your impurity will start to interact both with massless modes and massive modes. And what are the consequences of this? We wanted to analyze a little bit. And of course, there are two regimes. One is that the interaction with the impurity is much smaller than the gap in the transverse sector, in which case you can ignore this sector. You only know the sort of symmetric sector, and then it's very much like a single chain with renormalized parameter. And we find again the Green function, blah, 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 which is the power law with an exponent, which is the renormalized exponent, where only the Luttinger parameter of the symmetric sector is important. But you have also another regime where this time the interaction with the impurity is larger than the gap in the anti-symmetric sector. And then you can excite things. The impurity is perfectly allowed to excite this massive mode. And this changes the regime for the behavior of the impurity. Here it's only plotted at p equals 0. And you get potentially different exponents in the second regime due to the ladder nature of the system. So here is determined by a numerical method. What is the exponent, for example, as a function of the interaction u? Again, this red line that you see is this interpolating formula, which seems to work pretty well for surprising reasons to give you the exponent. One surprise that we got looking at the numerics is that we find that this exponent is increasing when we increase T-perp. And this is very surprising because if you look at the Luttinger liquid parameter, which was determined by Wu and collaborators, that they were kind enough to share this data with us for the ladder, you find that actually the Ks is decreasing when you increase T-perp, which means that by all naive expectations, you would have expected this parameter here to decrease when T-perp is going up. But this is not what is happening in the numerics. So there are definitely things we don't understand for the ladder. So I will leave it that way. But the ladder seems to offer new physics that we are not understanding. We see also the two regimes, namely the what I would call the quasi-particle and the infrared dominated regime in the ladder. And then finally, one subject I will not touch at all, which we just scratch the surface, is what happens when we also let the impurity hop between the legs. Now the impurity acquires some internal degree of freedom, if you want. You can imagine that one leg is spin up, the other is spin down. And this is a very interesting problem, but both very difficult analytically and very difficult numerically. Okay, I think my time is nearly up, so I won't spend, as anticipated, I won't spend much time dealing with the fermionic type behavior. But I just want to point out where is the catch with the fermionic quantum bath is that now you don't worry about this term, but you worry about the other term, which is this cosine 2 phi term. And then when you try to couple the impurity, we did it with n bath, you have something which is very much the same for the bath, but the part that remains for the coupling to the impurity is now containing this cosine of x, where x is the position of the impurity. Here, this little x is now replaced by the operator x of the impurity. And then you get a very complicated, oops, there is a tau prime. You get a very complicated and nasty looking Hamiltonian, which has this nonlinear coupling between the position of the impurity at two different times. Here, I just wrote the equilibrium version, the one in imaginary time. And you see that this interaction between the two times is now decreasing as a power law that you control with the Luttinger liquid exponent of the bath. So this is a completely different problem. And this problem is reminiscent of a certain number of problems in statistical physics, like long-range XY models and so on. And this type of things offer very exciting possibility to tackle this physics. So I won't go into detail. We did some RG analysis with Barbara Horowitz and Pierre Ledoussal. This has very interesting transitions between localized and delocalized regime. This has, for theorists, a delightful renormalization group that you can determine as a function of the number of paths to which you're coupled. I think my time is not allowing me to go in details of this, so I won't discuss much. One last element that I wanted to mention in terms of systems offering very interesting possibilities, perhaps less for cold atoms because of the local nature of the interaction. And we studied with Anne-Maria Visuri and Päivi Torma is what happens when the bath has really a structure. You put the nearest neighbor repulsion, for example, and then this charge density wave that I was mentioning is really marked. And of course, you can think about a spin chain, or you can think about system with long-range interactions. And then you create an impurity at site 0, and then you want to know how this impurity is able to move. If you had a perfect crystal like this, totally motionless, then that's very simple. Because you work at constant energy, the only place where this impurity can jump is the next occupied site and the next occupied site. So it's like moving in a band, and then you see in the periodic, you see band motion of the number of doublons, where the doublons is dissociated here, then reassociate, then dissociate, then reassociate, and so on and so forth. I don't know if I've lost my mic. But of course, if now you reduce the repulsion between these things, then what happens is that this very nice totally periodic motion is having still some periodic component, but depending on the values, is also leading to destruction of the number of doublon, where the impurity sort of dilutes everywhere in the chain. So this is also a very interesting set of problems that one can study. So I want to stop here. I don't think I have much to say in terms of conclusions. There are only 2 items which are important. So I hope to convey that we have very fascinating problems for what I would call out of equilibrium impurities in 1D problem, beyond determining the polaronic parameters. And I think there are many open questions, more open questions than there are closed answers. But there are also some of these answers that would really need to be tested in the experiment, which I'm sure would bring, again, new questions. And the last part is we need experiments, both on the bosonic and the fermionic side. And on that, I will stop and thank you for your attention.
Thanks for the talk. Amazing. So I just got myself thinking. So in your universal formula that you got for this, let's say, logarithmically modified diffusion, when you have, if you do simply, I mean, it surely describes not the whole g of xt, but some asymptotics, right? But if you nevertheless do the Fourier of it, would you get your effects that you observed with Kantian as a function of p?
The finite p.
Yeah, because you have in xt, and it was universal expression. Now, if you just do Fourier, I wonder whether you start to observe.
That's a good question. My recollection is that when we did the saddle point on this one, what we got is this one. So actually, we did the opposite. We started with this one.
Right now. Okay, fair enough. So here you can ask, if I do just Fourier of omega, would I get some different regimes of decay?
Good question.
I think you would, because the formula is universal, and the only question is how much asymptotics is important for Fourier, because it might.
Yes.
Yeah. So that's. But otherwise, I think you would recover it. Yeah, thanks.
Okay. Good. Something to.
Okay, online people also join us.
May I ask a question? Can you hear me?
Yes.
Thank you for the interesting talk. I had a question regarding these 2 regimes that you mentioned. One is infrared dominated and another is quasi-particle. You mentioned. Could you probably just give a bit more intuitive picture? How do you separate them, and what is actually the parameters that?
Yes. So essentially, one way you can see them is the behavior of this function R of u that I was mentioning in the link cluster expansion. So this will depend on what are the solutions that you can get here for this delta function here. If the only sort of solution that you get for this delta function is essentially around q equals 0, then you will get the first behavior. If you can find other intersections of these three dispersion relations, then you will find that your system can excite real excitations in the bath. So if you want, when your impurity is moving, it's able to really excite a phonon. Actually, you can do a slightly better job for this, which is really the perturbative calculation. You can use the real structure factor of the system. And actually for this, I can thank directly Jean-Sébastien again, because he gave us the data on the real structure factor of the Lieb-Lininger system. And actually, if you inject it in this formula, not this one, but you replace this sort of difference of bare energies by the real structure factor, you get very good agreement with the numerics you get out of the Giamarchi. But the difference is, again, something which can only excite virtual phonons, if you want, in the bath, and something which can really excite a real phonon in the bath.
Thank you.
Just a quick follow-up question, but
yeah.
But still, the parameters that distinguish these two regions is P, right?
Parameter. One way to go from one of this region to the other is to change P. Yes, absolutely.
And then one can ask favorites Vadim's question, whether it's sharp transition, whether it's crossover.
If you take seriously the link cluster expansion, it's a sharp transition.
Okay.
If you take the numerics,
yeah,
you see something which looks pretty sharp in the numerics. The exponent seems to collapse, and then you see some, but there, okay. We would need really an analytic solution to answer this question. I would say seriously.
Yeah.
Between a sharp crossover and a real transition, it's always delicate to answer.
So thanks for the nice talk. A question on the sign of the interaction. So you probably have been discussing repulsive interactions for most of the case. And where is there some symmetry with respect to attractive interactions, or where is the situation different for attractive interactions?
Indeed, most of the things I said, at least for bosons, this was for repulsive interactions. Very often also simply because, in particular, for example, in the works together with Misha and Vadim, very often we took the same interaction for the bath and for the particle because of wanting to respect the kind of SU2 symmetry for the system. So if you change now and put attraction for the bath, it's a catastrophe, and we would prefer to avoid it. There are a few studies where you can change attraction and repulsion, for example, the numerics on the kicked impurity, and of course for the fermions. And then I would say it depends on which precise problem you have in your mind. If I look, for example, at this thing that I was mentioning here for the fermions, you see K equal 1 is the non-interacting point. And if you go this side, you're repulsive, you will get this physics. But if you go on the other side, then you will get the attraction, and then you're dominated by the Q equals 0 part of the interaction with the impurity, which gives you completely different physics. So the change of sign of the interaction, this is between the molecules of the bath, can be dramatic. The sign of the interaction between the bath and the extra particle, I would say, is usually much less dramatic. Much less dramatic. Actually, for the periodic system, we studied also both the repulsion and the attraction, and very often you get practically symmetric. But again, this has to be discussed on a case-by-case basis.
Any other question?
Not from our online people. Okay, I'm stopping recording. Thanks to Thierry.
You.